Okay, thank you very much for the introduction. So I will talk about, I will focus on the computational part and the statistical part of the Tandem mass spectrometry data analysis. So first, just let's talk a little bit very briefly about Tandem mass spectrometry. So it's an instrumentation used for identify molecules, small molecules, bigger molecules in a complex sample. And but the bigger molecules could be as big as a protein molecule with a couple of thousands of Dalton. But earlier, the molecules were small molecules like water or ammonia and these kind of smaller molecules. But later, the instruments became very accurate and robust and sensitive, so they were able to analyze larger molecules, such as a peptide, organic molecules. And this makes the data more complicated, more complex, and we need the computational methods and computational algorithms to automatically annotate these data. So actually, just a couple of months ago, maybe a month ago, there was a study coming out which showed that they used mass spectrometry to identify, and they found nanoplastics in human blood. So this is a very bad news. Nanoplastics are the Teflon and PFA and these kind of molecules. And unfortunately, the microplastics are already in our food, and it turned out the nanoplastic molecules can be found in human blood, unfortunately. The good thing is they use the mass spectrometry to identify these plastic molecules in the human blood. Okay, so what I'm going to talk about now, I will talk about the spectrum annotation, how the spectrum is annotated. And then we will talk about how the machine learning methods can be used to improve the results. And finally, I will briefly mention that what you should be careful when you are using some machine learning based methods in mass spectrometry data. Okay, so what is a spectrum and how do we annotate the spectrum? So basically, the question is that we have an experimental spectrum, what you see on the screen here. And the question is that what is the data or a biological molecule which is responsible for generating this observed spectrum? Okay? Well, you can say anything, but the more important question is that, like, how and why and how likely is this annotation correct? Okay, so it's very likely that this experimental spectrum was generated by this HEEIDL peptide sequence. And if I look at the annotation there here, this annotation seems to be quite correct for my eyes. But someone always could argue that, no, this was observed by a chance. The correct peptide would be something else, something different. So in this field, we can never be sure that what's correct. We don't have 100% accuracy or 100% accurate training data. The reason is that we can never be sure that, because we cannot go into the instrument with our naked eyes, we cannot observe what are the exact molecules being generated, and this spectrum was generated by this exact molecule because I can confirm it with my naked eyes. No, it's not how it works. Unfortunately, we need to use some tricky statistical approaches to validate our experimental results. So one way is to use statistics to validate the results. Another approach is that we can also use a specific experiments to validate the statistical results, to make sure that the statistical results work properly. Okay, so one of the most commonly used approach to identify an experimental spectrum is this database searching. So basically, if we have an experimental spectrum S, we find we have a reference set of peptides from a database. We can generate them, and we annotate the experimental spectrum with the peptide sequence from the reference set, which produce the best score, matching score or similarity score between the two. Okay, so here I simply mean that the experimental spectrum is annotated by the peptide from a reference data set, this one, which produced the highest score. The CP refers to the candidate peptides, and basically it's some technical selection of biologically, chemically plausible peptides, candidate peptides. This is not complicated, it's just some technical things. We don't need to compare or search an experimental spectrum against the whole data set. We can always just search against the small fraction of a data set. So if anytime you have question, you can interrupt me anytime, and you can ask at the instant moment. Okay.
So you're now saying that you reduce the database DB based on additional information you have.
Yeah.
So what's this additional information?
For example, precursor mass filtering. That's a strong one. Or if you don't compare like the taxonomy. You don't consider, let's say, peptides or proteins from plants if you are working with human blood sample. Okay, something like this.
Okay, and previous question, you say you cannot have 100% accuracy training data.
Yeah.
So, but you can create molecules and put them in the machine yourself.
Yeah, but there will be always some noise. There can be some contamination from the air. There can be some contamination
but the contamination is proportional to the magnitude of the spectrum. The more you put in, the higher the spectrum, or it's not true.
It wouldn't ever be 100%.
Yeah, of course, but you can say that within 1% error, you should have the spectrum.
In 1% error, we can be very accurate.
Yeah, but the difference you show it's a huge difference, 50% error.
No, why would it be 50%?
I see a blue line and a purple line, and they in the middle at 900 hertz, and they differ by more than half.
I don't understand what
so at 1000 megahertz, you go one tag to the left, and there is a purple and a blue line.
This one.
1000, one at the left.
Okay, this is MOSFET charge, and how what's the
also this left? One differs a lot.
Here?
No, at 1000 hertz. Things are very different between blue and purple.
Oh, that's yes, and
so it's much more than 1%. So you can know the correct answer.
No, this is one annotation. This is a real experimental spectrum.
Yeah, so maybe the problem is I don't understand the graph here.
Okay, so here you have an experimental spectrum here, right? And then you have one peptide molecule, this one, and actually this one is one ion series, and this one is the other ion series, but this is the same. This is the same molecule. Okay. So this experimental spectrum is very likely to be generated by this very exact peptide sequence, or the molecule of this peptide sequence, right, Bruno?
So you say two molecules are the same. I'm more confused, but also I'm a bit tired today. So yeah.
Okay. I'm sorry. So this is one experimental spectrum, and this experimental spectrum is all the peaks here. Okay.
You observe all the peaks, and you have to assign each peak to one of the two molecules. That's your task.
No. Here I have this molecule, one molecule, and this is a fragmentation of the molecule. Okay, this is not hertz. So it's basically the distribution of the masses of the fragments of this molecule. You break this molecule, Okay, and then you get these fragments and you observe the distribution, let's say.
So what's on the horizontal axis?
The mass per charge of the fragment ions. The fragments.
Say it again.
This
mass
per charge, basically. You can consider it as a mass of the.
Sorry. Yeah. Okay. I was thinking about light spectrography. Yeah.
No,
so they're charged particles that bend in a magnetic field.
Yeah. Yes. Exactly.
Okay. Yeah. Now I got it.
Okay.
Yeah.
Okay. So here we go. So where was I? You had two questions and I answered two of them, right?
Yeah. Indeed.
What was I saying before? Okay, just to give some idea, usually we have a couple of 10 millions or few millions or 10 millions or hundreds of millions elements in the reference set. And when you use these candidate peptides, it can reduce the candidates for a couple of tens till 100 or thousands, or if you have work with a large modified peptides data sets, then maybe you have a 10,000s, tens of thousands of candidate peptides. So this reduces the candidates by a couple of magnitudes. We also need this score function here, which is basically takes an experimental spectrum and the peptide, a reference, and an element from the reference data set, and it gives us some kind of real-valued scoring function to evaluate the similarity or the match between the experimental spectrum and the peptide from the data set. Okay, so what we expect, we don't have lots of restriction on this scoring function, but what we expect is that it gives us, for a more likely match, we get better score or higher scores. Okay, so now I'm talking about this very same things, but with a visual form. So we have thousands of or millions of experimental spectra from one instrument, from one experimenter. And then for one experimental spectrum, this one, it's just enlarged here. It is compared against a set of candidate peptides. The candidate peptides here are marked with green, okay? And then you generate some kind of theoretical spectrum from this peptide sequence, and then you match this observed experimental spectrum to this theoretical spectrum. So how can we calculate this theoretical spectrum if we have a peptide? So basically we know the fragmentation rules from chemistry. We know the mass, the monoisotopic or the average isotopic masses of these amino acids. And we can calculate what could be the theoretical fragmentation of this peptide in the very ideal case. Okay? So this would be the very ideal theoretical spectrum for this peptide sequence. Okay? Here you can see the B ion series, you can see the Y ion series. And here we don't have intensity because we assume that all the fragment ions would be observed the same intensity. Okay, so this would be the experimental spectrum. And what we need, because the location of the peaks are real valued, okay, so these are not, and the location of the peaks in the instruments might have some inaccuracy because of the inaccuracy of the detectors. So we need to kind of relax on the matching, so we cannot exactly match peaks, real valued peaks to another real value because there's an instrument inaccuracy. So we need to discretize first the spectra. So basically we divide the x-axis in the horizontal axis into small bins, okay, and then we get some vector, and the value in this vector, it measures, or it is the sum or the maximum of the intensity of the peaks which fall into that given bin. Okay, so basically the experimental spectrum is represented with a discretized real valued spectrum vector. Okay, so now we discretize the theoretical spectrum, then we discretize this experimental spectrum, and then we just measure, match for example, we can evaluate the match by counting the peaks at the common location. For example, here there is a match 1, 2, 2. So here 2 peaks, this one and this one, this one, this one are matching. The other peaks are off by some distance. Okay, so this is basically the core of the calculation of the matching of the experimental and the theoretical spectrum. Okay, you can, of course, there are more accurate scoring functions. For example, you can take into account the intensity of the peaks. So you can measure the similarity or the match of the experimental and theoretical spectrum by the sum of the intensity of the matching peaks. It would be a little bit more accurate, or it would give you better results. Okay, so how do we annotate one spectrum? So the experimental spectrum, this one, is going to be annotated by the peptide sequence which produces the highest score, highest matching score. Okay, the problem is that every spectrum will be annotated by a peptide sequence, but it doesn't mean that the annotation is correct. And in practice, roughly like 50–80% of the spectrum data cannot be annotated correctly with high confidence. And there can be lots of issues, like the scoring function isn't smart enough. It doesn't discriminate well between the correct and the incorrect peptide spectrum matches. There can be the normalization is not good enough. There are some experimental spectrum which has many peaks. The other experimental spectrum has a few peaks. Maybe your statistical correction or some, you should also use some statistical correction or some other advanced statistical approaches to get some better higher confidence. And probably the biggest factor is that the candidate peptide set is incomplete. Maybe it does not contain the correct peptide from the reference set. It can be maybe due to some post-translational modification. There can be some other chemical contamination in the samples. It can be that the sample preparation didn't go well. Maybe the energy in the instrument was too high, it broke the peptide, and then the spectrum already corresponds to some garbage. Okay, so what we do is basically we can order the spectrum annotation by their score in decreasing order. You remember that the higher score indicates a better or more likely correct annotation between the spectrum and the peptide. We can order them by scores. And then the question is that where can we put this decision threshold so that the error amount here, so we accept these, the error among these annotations is some at a fixed level, fixed rate, for example, 1% error rate or 1% false discovery rate. Okay, so we can do this. So let's take a look at again this database searching. We remember that we match one experimental spectrum against a set of candidate peptides, and we can collect these scores, these matching scores. So for example, for this one, we could get 1, 2, 3, 4, 5, 6, 7, 8, 9. We could get 9, but in practice, we get a couple of hundred scores here. And then we can create a histogram from these scores. So if there is an experimental spectrum which is correctly annotated, then there will be only one of the peptides can be correct. Either each of them are incorrect, or just at least there's one peptide which can be correct. Okay, so then we can define this discriminative power. It's basically the top scoring, the score of the top scoring peptide is the difference between the score of the top scoring peptide and the rest of the scores, histograms. Okay, so because these scores are coming from incorrect batches, so these can be referred as the null distribution, some empirical null histogram. Okay? So the discriminative power scoring function is intuitively, not mathematically, intuitively, it's basically how well the score of the correct annotation is separated from the random matching scores. Okay? How can we improve the discriminative power of some scoring function? It's very technical, but for example, you can also introduce or consider some additional peaks. So this is very technical, but there can be some secondary fragmentation peaks. For example, if you find a peak corresponding to a fragment ion, usually you can also find some other peaks closely related to the main peak, but maybe it differs from the mass of ammonium or a mass of some loss, etc., etc. And also you can include double charged peaks, single charged peaks. It's very, very technical, but basically you can improve your scoring considering these more closely related peaks to the major or the primary fragmentation peaks. The second thing is that for some experimental spectrum, for example, a score of this 2.7, it seems to be quite a good score compared to the null distribution. But if you take another experimental spectrum, for example, for this, the null distributions is spread over a larger range. For example, for this experimental spectrum, a score of 2.7 doesn't seem to be that significant. Okay? So we need a kind of score normalization. And basically, the score normalization is related to the p-value. It tells you how significant your hit is. Okay? There are lots of approaches. So in the beginning, in the 90s, researchers used like analytical approaches. They assumed that the null distribution follows a binomial distribution, and then they wrote a paper about this. But then later they figured out, no, the score follows hypergeometrical distribution just by simply looking at the shape of the null distributions. Then they wrote a paper about this. Then they figured out, it follows a normal distribution, and then they wrote another paper. Later, there more data-driven approaches came into the game, and they decided to fit a linear regression line on this, or the logarithm of the scores. And this is the comma t-values and extended values. They try to fit a linear line on this part of the null distribution. And when you have a hit, basically you evaluate the score or you evaluate this linear line at this position, and then whichever you get here, this is considered as a e-value. Okay. For example, if you have a PSM score around here, for this the e-value would be around -1, which is. Then there are the exact p-value approaches. It's used in MSGF plus or tide search. They are effectively enumerate all the possible peptide sequences. They calculate the score, and they will get a very, very fine empirical null distribution. So they are not using only just 100 or 10 or thousands of scores from the candidate peptide list. They effectively enumerate all the possible peptide sequences. and they build a very fine empirical score distribution. And basically the E value or the P value of a hit is calculated like the fraction of the matches which achieved a higher score than this given than what you observed. Okay, so then computationally it wouldn't be feasible to enumerate. So they use dynamic programming to avoid redundant calculations, and they directly calculate the score distribution using dynamic programming. It's computationally much slower. It's like 10 times slower than other approaches, but the results are significantly better. They are very good. There are other methods, some heuristics, which are not related to Pvalues. This is the X-score and Taylor method. These are some fast but some heuristic score calibrations. Okay, so the Pvalues, the previous methods, these aim to provide an empirical P-value, which, just remember, it's an estimation of the true but unknown P-value. So the estimation can be either your estimation is consistently provide higher values than the true and unknown P-value, then your estimation is going to be conservative estimation. Otherwise, if your P-value calculation provides consistently lower values than the true but unobserved P-value, then you will end up with a liberal estimation. Okay? So, but how do we know that if our method is conservative or liberal? So we know that if we have a null distribution with sample according to this distribution, we calculate the p-values, right? And then we plot the p-values, then or make the histogram of these p-values. These p-values should be uniformly distributed. Okay? So these are the p-values from one experiment, malaria experiment, and I used to calculate these p-values with this exact p-value methods. And if you put these scores on the p-values on the QQ plot, then the p-values, the p-value versus the ranks should follow this linear pattern along the diagonal. Okay. For the analytical methods, so that it means that the exact p-value calculation is quite accurate in practice. But if you use other p-values methods, some analytical methods from another program, for example, from the OMSA, which uses a Poisson distribution, and then you plot the p-values, then it looks like it's more like biased. Okay. So then the p-values from the OMSA toolboxes, they aren't that accurate, and they consistently provide lower p-values than they should be, right? Which leads to, I think, to liberal estimation. Okay, so another question is that still we didn't get closer to our aim. So the question is that how can we put this threshold so that the error among the annotation or our trusted annotation is at a certain level? Usually, in practice in this field, we use the false discovery rate. Okay, so we would like to set up the threshold so that the incorrect spectrum annotation are at a certain user-defined level. The typical levels are either 0.1% or 1% or 5% at most. I think 10% aren't really trusted anymore. So how can we get an estimation on an incorrect spectrum annotation? So I'm going to talk about two approaches. One of them is the target decoy approach. And in this case, we consider the peptides from the reference datasets as target peptides. And for each of them, we randomly generate a so-called fake or random peptide sequence. We mark it. That's a decoy peptide. Okay. For example, the decoys, you can either shuffle the amino acids in the peptide, or you can reverse the non-terminal amino acids in the peptides, and they are good enough to be decoy peptides. Okay, there is one restriction, that the main characteristics of the target and decoy peptides should be similar in terms of the amino acid frequencies, the length of the peptides, the neutral mass, or like the mass or the distribution of this peptide. So the main characteristics shouldn't change, and the amino acid shuffling or the peptide reversing, they wouldn't change the main characteristics of the target and decoy peptides data sets. Now we have an assumption. So if you do the database search and then you find in the output one spectrum annotated with a decoy peptide, then we assume that there is another incorrect spectrum annotation annotated with a target peptide with a similar score. Okay, so now here I added decoy peptides, and the decoy peptides are marked with asterisks. Okay, so in this output we found 3 decoy peptides. Okay, so we have an assumption that here among this there are 3 other incorrect spectrum annotation with similar scores. Okay, so for example here there is one decoy peptide, so I assume that around this region there is another spectrum annotation annotated with target peptides, but incorrectly, and they have a similar score. And here they are also, the same goes for this. Okay, so if I plot the scores from a real experiment, then the scores of the corresponding to the decoy peptides are this one. Okay. Then we have a very similar score distribution, which are corresponding to spectrum and target peptide matches, but most likely they are incorrect. Okay. And then we also have several spectrum annotations here. They have more significant scores. Okay. So now the question is that where can we put this threshold so that the false discovery rate in this region is, let's say, at 1%. Okay, so in this very example, the threshold should be around 3.1327. So then the false discovery rate here would be 1%. Okay. So that's why the discriminative power of scoring function is very important, because then the scores of the correct spectrum peptide annotations would be higher. So you would get a mode for the correct peptide spectrum annotations here. Okay, now I'm going to talk about the second approach. It doesn't require decoy peptides, but it requires a very well-calibrated p-values. And then you can control the false discovery rate with this Benjamini-Hochberg protocol. Okay, so remember that we discussed that if you have samples from the null distribution, you calculate the p-values, they should follow, those p-values should be uniformly distributed. And if you plot those p-values against their rank, you would see some kind of diagonal line. Okay? Now, if you have, this is the same. Now, if you have some spectrum matches which are not coming from the null distribution and they are ranked at the beginning, then in that case, this plot would look like something like this. So I'm just using the target decoy just merely for illustration, okay? So that you can see that here indeed the target peptides are ranked at the very beginning, okay? And then they have very small, teeny tiny p-values. And then the decoys, which are coming from the null distribution, they are more likely, more or less uniformly distributed. Okay, and this this, okay, let's talk about it later. Okay, so now I'm going to zoom in into this part, okay? And then this is the very same plot, just I zoomed in this part, and you can see that here we have the targets. And then after a while, the targets and the decoys start appearing, and we get more and more decoys. Okay, so now this plot, I will change the linear scale on the y-axis here to logarithmic. So we can see here the p-values of the possibly correct peptide spectrum annotations. It looks like something here. So we have really nice p-values that we could accept. Now, in the Benjamin-Holberg procedure, we want to control the false discovery rate at a certain error rate. So we can plot a line. This is kind of decision line. Okay, and then this corresponds in this area example, it corresponds to the alpha level of 5%. Okay, so all spectrum annotations which are below this line, they are accepted or trusted. And then the incorrect annotation here, it has 5% in ratio. So this is how it looks. Now talking about the results validation, how it looks in practice. In practice, we evaluate the performance of this database searching methods like this. Here we put the estimated false discovery rate. Okay, like it here I control the false discovery rate at 0.1%, and how many peptides I got at this given false discovery rate. And then you can calculate the the number of the annotated spectrum at 1% false discovery rate. You get more peptides. You can get more annotations. Okay? So basically, the higher curves, higher the curve is, the better its performance. Okay. So this was the end of the first section. Now I would like to talk about some machine learning.
Sorry, and could you repeat again on the last plot what were the different lines?
Yeah, it's a very good question. Sorry. So different lines correspond to different methods, different database searching programs.
Okay. I see.
Okay. So this one was obtained with MSM, and I think it's implemented or developed by some Austrians. Don't know where. Then the X style doesn't look well, doesn't seem to perform well. This dot one corresponds to the OMSA program. This is the one which uses Poisson distribution for calculating the p-values. It's a little bit better, but still not that good. This was developed by NIH and CBI from United States. Tandem is from Rockefeller University, I think, from New York, developed by David Fennieu. It was it's around 20 years old program, and that uses a linear regression line to fit on the slope of the empirical null distribution to calculate some e-value for the annotations. Okay, then this one is the MSGF+. This is a method developed by the team of Pavel Pevzner from San Diego. This is a Russian guy from St. Petersburg, but now he lives in San Diego, and they are also doing very well. The X-score is a scoring function with exact p-value score calibration. It seems to outperform the other methods. And then this black one is developed by us recently, and I'm going to actually talk about this sports much.
I see. Okay, thank you.
All right. Okay, so let me talk about some machine learning. How can we use machine learning for improving the scoring? So remember that I showed it to you that we can introduce, we can add, or we can consider some secondary fragmentation peaks in the scoring function. For example, the X-score, it adds a weight 50, if a peak matches to the primary fragmentation peak, but it adds a weight of 25 if the peak is matching to some flanking peaks. Okay, here the difference between the major primary fragmentation and the flanking peaks is usually it's a mass of one proton, and they might correspond to isotopic errors, so some isotopes. And then it also can consider weight. Maybe this is a carbon monoxide loss or ammonia loss or water loss. And this way, this match is weighted by 10. Okay, so this is the X-score scoring function. It has this more advanced scoring to increase the discriminative power. So what we did, we designed, okay, let's connect everything, everybody with everybody. So here we have a fully connected layer, basically. This is a weight matrix. Everybody is connected with everybody. And we use machine learning to calculate the weights of these. So in the X-score scoring here, the weights were manually calibrated around 30 years ago by now. And they were calibrated 30 years ago, and they are still using the same weights. But now we can learn actually from the data these weights for the optimal weights. So we use the Boltzmann machine. So basically, this is a Boltzmann machine. Here we have the observed data. This is the hidden data, the unobserved data, and we consider the theoretical peptides as the responsible cause for generating this experimental spectrum. Okay.
So in the old method, 4 weights were manually calibrated, right? 10, 25, 25, and 50.
Yeah, they did it manually.
Yeah, so just 4 weights were calibrated, right?
Just what? Just
4 weights were chosen, or how many weights were manually calibrated?
So the primary, the main one is 1. Then you have flanking peaks, and then for the auxiliary, you can consider carbon monoxide loss, ammonia loss, and water loss.
So it's about 6 parameters.
6, kind of.
Yeah.
But you can also you can also add more. For example, Z ions and C ions and all kind of stuff.
Yeah, but it's very robust method. I mean, if you change the machine, it's probably still gonna work.
Yeah, it does.
And you will calibrate a huge number of parameters, but then does it work among different machines and different setups?
Well, that's not, but you will get much accurate results.
Yeah, but you need to train it for individual runs, I guess.
Yeah. Okay, let's talk about this later.
Okay, yeah.
I will address this.
Yeah.
Okay. Actually, yeah, you're right. So here, usually we can observe the range which goes from 0 to 2000. And then if you discretize the horizontal with integer, with one mass of the proton, then you will get a component of 2000, right? And then you do the same for the theoretical, then you will have 2000 times 2000, you will have 4 million parameters, right? But if you have a high resolution instrument, then here you have 100,000 beans, and 100,000 times 100,000, it's a lot, yes. But you can still actually read. The good thing with mass spectrometry, we have plenty of data. That's not an issue. Okay, let's go back. So this is the scoring. There is basically the scoring. In this model, we model the joint probability of that the experimental and theoretical spectrum were observed together. Okay? And then the weight is this middle layer, which is going to be optimized with some machine learning data. Okay. And actually, this model is interpretable. So if we show the heat map, some part of the heat map of the weight matrix, this W matrix, then you can see biologically plausible explanations. So here, this diagonal line, it corresponds to the weight of the correct matching peaks for the primary fragmentation peaks. That means that the peaks were in the same position. And you get this other here. Then you can also see some off-diagonal lines here. They correspond to some losses, like I think this is these here. There are two lines actually, and they correspond to water and ammonia loss. And these at the C, these are the peaks which are one amino acid far away from the middle position. Okay, so then here we have one amino acid, and then this is the subsequent and the neighboring amino acids. So you can find the peaks which are one amino acid far away. And then we have this skewed diagonal, and these correspond to double charged peaks. Okay. So we can get this very. So this shows that the model did learn. Actually, the model did learn the chemical and physical fragmentation patterns from the data. And then when we run it in the experiments, we can get this. Our method is Boltzmann scoring. The scoring based on Boltzmann machines significantly outperform the other methods. Okay. One way to improve this model, and actually we did it, because this indeed it's very difficult to train and takes lots of time. And actually, if you keep training, you need to stop the training after a few epochs, because then it overfits. To improve the computation, improve this model, we don't need to use a fully connected layer, but we can use actually a convolutional layer, like a convolutional, one-dimensional convolutional layer, because actually it's just a sliding window going over, like basically here there's a sliding window going over the experimental spectrum, because you don't really need to consider this peak and then something at very far from each other, because probably there is no stronger correlation. But with the convolutional neural networks, you can have just 100 or a few thousands of parameters, and it focuses only locally to the region, some neighboring region in the vicinity of a peak. And then it's much robust to train than this Boltzmann machine. Okay, one of the last part I would like to discuss is this pitfalls in machine learning, and it's related to the bias, this machine bias. And actually, if you are not careful, then the machine learning model can acquire preference toward target peptides. Right? And then if a spectrum is matched with the target peptides, it will just give a little bit better, higher score for that spectrum annotation compared to when the spectrum is matched with decoy peptides. Okay, so then in this case, the target peptides will be preferred by in random matchings. So then it will violate some of the assumption in the target decoy approach. And as a consequence, we will get a biased false discovery rate estimation. Okay, and now my question is that, is it going to be conservative or liberal false discovery estimation? That's my question to the audience. Okay, is there someone thinking? Yeah, Bruno.
I was trying to recall. Conservative means too high p-value, or
the conservative means that the false discovery rate actually is lower than the actually. Conservative is like strict, it's like strict, and the liberal is more like
false discovery rate is lower. And so in machine learning, I would guess since No, I don't know. I don't know anything reasonable to say.
It's always
it's overfitting, and so that's what you're talking about, right? So it will be too conservative, I guess.
Liberal.
Liberal. Okay.
And it just means that the false discovery, the actual false discovery is much higher. Then your error can be 5%, but your evaluation says the error is 1%. Okay, that's a good one. It's just good to hear something from you. Okay, actually there is this Percolator. It's a computational tool. It's a post-processing tool. It was published 13 years ago, and it extracts around 10 or 100 features from each spectrum peptide match. For example, it extracts information about the type of the peptides, what its cleavage site, does it contain modification, what's the difference between the precursor mass tolerance, etc., etc. And there can be lots of biological features extracted. So it turned out that some of the features can leak information whether this spectrum is annotated to a target or decoy peptide. Okay? And then it turned out this Percolator exploited this information and provided better results than it was actually doing. So what we did, we corrected these features, and it looks like then if you correct the features, then the Percolator isn't producing that well. If you correct this bias, okay, the original Percolator gives this orange performance, and if you correct these leaky features, then you get a little bit less number of accepted peptide spectrum matches. Okay, well, the error is not that tragic, but the bias was there for 10 years, and it's been identified. Okay, well, that's all I wanted to share about my research. And if you have any questions, I would be happy to answer.
Yes, thank you very much. So other questions? I actually have one. So could you go to the part 2 where you showed the matrix of weights?
This one?
Yes. So you've also okay. The first question is, was it computationally challenging actually? Because you mentioned that you can consider like 10,000 or something like this.
For
matrix of size 10,000 times 10,000 is already like do not fit into probably fast memory or something like this.
So we used GPUs, and then if with low resolution data, actually there was no problem. It was 4 million, and it fit in a GPU's memory.
Okay. But are you interested in high resolution, or is this enough for application?
No, for high resolution we needed like 100. We calculated like we needed 100 gigabyte of memory or RAM, and that was trained in CPU.
I see.
And in our data sets, the whole training for one data set on a CPU for high resolution took 1 day. It was, okay. I think it was doable.
Okay, and then you also mentioned that you can use convolutions here. So this basically restricts your matrix. There is some additional structure, which, as far as I understand, leads to like a matrix with constant diagonals and very sparse matrix also.
Yes. So basically, the convolutional layer, it goes over this part, right?
Exactly. So, but you cannot model this like skew diagonal part in this case, right?
Yes,
so
that's correct.
I see. So you maybe can combine somehow. It's what is it, strides or something like this?
What they do in practice, they can generate for the theoretical peptides. They can generate the double charged peaks. So you don't need that. You don't need this. And the training for a convolutional network in a GPU, it's minutes, 5-10 minutes.
But do you get worse quality in this case, or
actually slightly better.
Slightly better.
Okay. Slightly.
I see. So there are no computational challenges. So it's like you are satisfied with the performance of convolutional layers, for example.
Very much.
I'm also thinking if you can, because I have some like this background in structured matrices and so on, but
I see.
I can trying to find connections, something like this.
Yeah, I see.
Okay. Are there more questions?
So I lack a lot of background. My question is the user. What does he need to train?
Basically, you would need to train the model for each instrument, and you can pre-train.
And what about the other models you're comparing your method to? You also need to train them for each instrument.
Well, sometimes, for example, these are the standard methods like the MSGF and M7. That they are not trained. These are not training-based score functions, because there is no training. But you need to parameterize them still.
But that's just one value you have to choose. Like I have 2,000 bins or 4,000 or whatever.
Usually you need to choose the type of the instrument, and then it will start working with a predefined parameter set for each type of instruments.
Yeah. So what you do is, at the price of training individual machines, you can have higher accuracy.
Yeah, so basically we could do this if I developed this method as a software and I would distribute it, then we could get data from each commonly used instruments, train a model on that instrument, and then then distribute this pre-trained model, and then it could be used.
Okay, and when the user trains on his instrument, does it mean that he needs to make specific experiments and collect a lot of data on this instrument?
No, actually what we did, because this is a Boltzmann machine, it was all in the neural networks, we made the training more efficient with using annotated data. Okay, so here we run a basic search, probably this X-score, and then we took the peptide spectrum matches, which are very likely correct. Okay, and then we used it.
But still, my question: on which data does the user need to train?
Well, because we are not providing this as a toolbox. This is more like just a theoretical that you can. But if we provide it as a toolbox, we would provide the trained models. Then the user wouldn't need to train.
Okay. And you would provide for each machine. Okay, but that's not the point of the research. The point of the research is to interpret this convolutional model or their variants. So what is the goal of the research then? I assumed it was to provide the user with better algorithms to understand the data better.
Yes.
Yes, but then he needs to train a model himself on some data.
Yes. So let's suppose next year someone creates a new instrument, then the model needs to be trained on that instrument.
Yeah, so he needs to collect data on this instrument first.
Yes.
And so how difficult is this?
I mean, the same way as you did it for the first time.
But for the existing machines, you can now collect on the internet, I guess.
Yes.
Data sets are merged.
Yes.
But if a factory makes a new instrument, it means he cannot use your algorithm unless he does a lot of experiments first, and then for the user provides the model. Yeah.
Exactly. So you need to calibrate the model for each instrument.
Yeah, and this is not a problem with the other models. So it might still be that the company uses the other models.
Well, slow down, Bruno. So we are using machine learning. Okay, and if you develop a model which does speech recognition, you shouldn't use this model for image classification. Of course, you need to train it for the best performance. You need to adapt the model to your data or the instrument.
Yeah.
Clearly, it's like in a four-wheeler racing. For each track, they adapt the car parameters for the track to get the best performance. If you want to achieve state-of-the-art performance, you need to adapt to the specific task.
That's sure. But I wanted to understand, okay, you show us some graphs and your method is clearly better, but that's what all people do. Now I want to know where are the catches, the little letters in the footnote. And so, okay, I said already 5 times. The footnote is that these other models, they work for all machines without training.
No, okay. So if you use the old mesh methods and then you are not using the proper instrument, you can still get a very poor performance.
Okay. And that's because you need to adapt the bin sizes.
You need to adapt the bin size. So most of the time, more or less, the fragmentation is the same for each instrument. Yeah. But there are some instrumentation technologies, which fails to observe the Y ion series. Okay, then you will get more B ions, and then this kind of types. But another instrument, and if you choose the wrong instrument for your method, then you will not get anything better. Yeah. But actually, with this whole methodology, if you take any of these methods, they have usually around 100 parameters.
Okay.
You need to specify the taxon, you need to specify the modification, you need to specify the protein database, you need to specify everything. And if you make big mistakes, you can get like 0 results.
Yeah.
With the old methods too.
Yeah, so you need still a really serious specialist to use them.
Yes.
Okay.